if you have not been paying attention all semester long, this is the week to start. All right? 3 or 4 weeks left, and now is the time to actually pay attention. Because what I'm going to do today is I'm going to teach you how to use statistics to test a hypothesis, which is my whole point of teaching this class, starting today. Okay? Lesson number 9. You are going to learn how to do the statistics to test a hypothesis. Because last class, when we talked about this idea of a distribution of sample means, what we're going to do today is we're going to change that to include not just the sample means themselves, but we're going to have this distribution of sample means also be the distribution of the difference of sample means. So if we have our regular normal distribution, this is the population, right? This is the population of all peoples. And this second distribution is the distribution of sample means, right? So we're going to be on the little line here, and we're going to say that of the population sample mean, of the population mean, that there is a sample distribution centered on the population mean. We're going to use just a little bit of inference here. And we're going to say, well, what if we have 2 samples from the population? So let me walk you through an example. I love this example. It's a good one, isn't it? Okay? And we can kind of, if we wanted to, collect some data. So let's imagine there's a world out there where you're really interested in how people behave when it comes to being in a parking lot. I'm sure there's some branch of sociology that uses this as their example, or psychology. Because I know it exists because this is based off of a journal article. So let me ask you a question. What type of person are you? Imagine you're in your car about to leave a parking lot. You're walking to your car, and you have that feeling that you're about to possibly be run over. Why? Because somebody would like to follow you to your parking spot. Have you ever had this experience? Yes, we all almost have had this experience. Here at Coastal particularly, right? When I was in graduate school at Michigan State, what we would do is we would just park our cars at the end of the row and wait for somebody to walk down our row, and then I've actually offered people a ride. Can I give you a ride to your car? Big parking lot, Big Ten. Right? I've done that before. Do you behave differently when you're being stalked? Yes? Okay. Do you, like, hurry up? Yeah. Yeah. Maybe you want to mess with them and, like, just wander through the parking lot, like, through the different rows. Like, oh, no, I'm not in this row. I'm in that row. And then watch them speed and turn. May have done this once or twice, okay? And then, like, oh, you think I'm in this row? And then you duck back through the cars and you hop in your car. Maybe even walk backwards. Like, you just want to mess with somebody. I might have done that to a friend of mine one time. All right. So does your behavior change based upon your feelings or your environment? So in the language of this paper, our question is, will people take longer to leave a parking spot when another driver is waiting? And the language of this has that other driver as an intruder. They're here to take your space, compared to when no other driver is waiting. So we have 2 conditions. All right? The parking lot out here is not really full, and now that it's gated, we don't have you people trying to steal our parking spots. You students trying to park in faculty staff parking. Thank God for the gates. All right. It's a little empty right now, so I can't really watch it. It's not always empty. Just right around noonish. All right. Tuesdays and Thursdays are rough. Okay. So how do we behave? So this is what happened. These people, Ruback et al., Ruback did a study where they watched people, and they timed them to see how long it took them to get in their car, turn it on, and get out of the parking spot. Right? A very simple thing. How long does it take? So they collected data. They had 15 observations in each condition, so that's a total of 30. Right? We have 30 observations. For the intruder, it took, on average, 40 seconds to vacate the parking spot when there was somebody clearly waiting for it. When there was no intruder, it took, on average, 31 seconds. So we have a difference between these two sample means. 15 cars, or 15 people in each sample. So 30 total. Take the sample and divide it under two conditions. One condition is those where there was an intruder waiting, one where there was no intruder waiting. So I'm not showing you the full data set for all 15 cars in each category. We've narrowed this down for you. So we know how to compute the average. It's just the sum of all the times divided by the number of observations. For this sample, we can compute a standard deviation first, and then a standard error. All right. For why a standard error? Because we're dealing with a sample now. Okay. And we can calculate these for the two conditions, when there is an intruder and when there's not an intruder. Now, if we look at the standard deviations, they're both about 10. But we notice that the intruder one is a little bit larger. So what does that mean? That means there's more variation in those 15 times. So you might have some person, again, thinking about a distribution, right? You might have some people that take extra long, like knowingly take extra long. Like, you've invaded my personal space, you've creeped me out, I'm going to make you wait an additional 10 seconds. Like, I'm not just going to put my seatbelt on, I'm going to adjust my mirrors, and we can get the radio station the way I like it. I'm going to turn on the air con, get the windows up or down. I'm going to check my mirrors a third time, and then I'm going to pull out of the spot. What's the other alternative? If you're like a nice human being and overly considerate of other people, how might you react if somebody is trying to wants to park in your parking spot? Yeah, you might actually hurry up. Like, they're going to wait on me. Hell with the seatbelt, right? I got the car started, my door's barely closed, and I've already got it in reverse. Right? And I'll pull out, and then once I'm out, I don't have to leave the parking lot. I can then, maybe put it back in park and adjust the mirrors 3 times and get the air con going, right? So I'll move quickly, right? There are some people out there, I think they're called considerate people. So we might actually expect a larger amount of variation when there's an intruder, right? It could speed us up. It could also slow us down out of spite. Or you just don't like people in those types of cars. Like, no person in a car nicer than mine needs a parking spot. I'm going to take my sweet-ass time. All right. So what have we observed in our sample only? Is there a difference between the two conditions? Yes or no? What is that difference? That people who have an intruder do what? On average, take longer to get out of the parking spot. By how much? 9 seconds. 9 seconds longer. Is 9 seconds a long amount of time? It will be if I stay silent for 9 seconds. 9 seconds is long enough to be uncomfortable, right? We hit 5 and we're like, okay, can this be over with? It's really not that long. Okay. All right. So we do have a difference. Now here's the question that we're going to ask. This is the question that we've been building up to with what we've learned about statistical distributions all semester long. We have to ask ourselves a question. Given the fact that we have a sample from a population, how likely is it that this difference also exists in the population? Because somebody in here is thinking, wow, that's all you need to science? Like 30 observations? I can do that in an afternoon. Doesn't seem like a lot. 30 observations to write a paper. How many parking spots do you think there are on Coastal's campus? Or a large mall? Or a stadium? Coastal doesn't have a parking problem. Coastal has a walking problem, which is also merged into a shuttle problem. But again, because you don't walk. All right? Think of all of the times that you get into a car and park in a day. Right? You get in your car. Nobody's probably trying to get into your driveway, so I don't think you can count that one. But you go to work, you go to class, you go get something to eat after work. Right? How many times are you in and out of your car in a day? A few. And add that up. Right? So there was a time when I left my house, I went to daycare, I parked at daycare. And then I left daycare and I came to work and I parked at work. And then I leave work and then I drive back to daycare and I park at daycare. And then I drive and pick up Abby at after school and park there. And then, my God, I just want to go home. So in a day, I can probably have, and that's not even to say if I'm really lazy and I'd like drive to a meeting off campus or go get some lunch or something. So each of us can have 4 or 5 times that we park in a parking lot. So what do we think is this a large population that we're dealing with? Right? This is one of those like really large, like the number in the lifetime of the history of cars and people in parking lot times hundreds of millions of cars on the road on any given day. There are a lot of examples of this behavior, right? This isn't like we only have 50 states. And I know you think Coastal only has 40 parking spots, but we know that it has lots. So we've got a relatively small sample, and I use that relative because 30 compared to the hundreds of millions. Right. Here's another thing that's sort of working against us. Some of you are from out of state. Do you notice geographical differences in how people drive? Okay. Would you like to share some of these irrational stereotypes with the class? We can start with Canadians.
The left lane is the right lane.
What's that mean?
Everyone drives slow in the left lane when they're supposed to drive fast in the left lane. They're supposed to go slower.
You know why people might be in the left lane? Because 3 miles later, they're going to make a left turn and do it without putting their signal on.
Yep.
Somebody actually yelled at my mom for driving in the left lane, and she was looking for the turn. Like, down 501. Like, you don't yell at my mom. She's kind of... Okay. So there are clearly geographic differences. I've noticed that in South Carolina, when you're making a right-hand turn, people think you need to stop and then make the right-hand turn instead of trusting momentum and allowing your car to actually just, go through the turn. What's that? Yeah, right. It's some part of some insurance scam. But they're also doing it while not putting their blinker on. So it's like, I will stop in the middle of the road, make sure my right-handed turn is clear, even though it would be clear anyways, because it's a right-handed turn. Yeah. So we all have this. So there probably is also some geographic variation, like local norms and customs. We could be at a college campus where when somebody's coming, you hurry up because parking is so limited and they're violent. Okay. All right. So we have in our mind, we can understand why there could also be some differences. We have a very large potential sample. Bar charts are dumb. Okay. So what have we done before? Well, what we did before when we were talking about sample means is we looked at the likelihood of our sample mean given what we know about the distribution in the population. And that's when we constructed confidence intervals last week. Right? How likely is it that given our sample mean that our confidence interval contains the population mean? Well, we're going to do something slightly different. We're going to look at the difference between two sample means and evaluate that difference. So here we have x1, which are our intruders. We have a sample mean. And we also have x2, which is the sample mean of no intruders. What did we observe? Well, we observed that the difference between x1 and x2 is what? 9 seconds, right? This is what we have directly observed. What if we treated this distribution of sample means that is contained as part of our population mean as a distribution of the difference of sample means? So we're going to look at the difference between two groups. This is the game changer for you guys, because now you can compare two groups. In this example, we're doing intruders and not intruders, or no intruders. For your course papers, you could do things like gender, race, although try not to be racist when you write that paper. Actually, just don't write about race. Sexual orientation. Yeah, stay away from that one too. You guys aren't really, well, you're better than some people, but just be careful, okay? People with college degrees and not with college degrees. There we go, safe. Right? So if we can classify people into, and I'm only teaching you today, two groups, we can look at the differences between those two groups. Now, when we do this, we're doing it in a framework of a null hypothesis. Remember hypothesis testing? The null hypothesis. And by default, the null hypothesis always says what about a relationship? Null. Yet. No. That there's no relationship. That's why we call it the null hypothesis. So we're going to see if what we've observed, which is a difference of 9 seconds, how likely is that if there should be no difference? So that's what we're going to do. We're going to determine the probability of obtaining a difference between two sample means. How likely is it that we get that 9 seconds if there should be no effect? Right? So we're really, again, I want to focus on that. How likely is it that we see a difference when no difference exists? Now, I have to caution you, because we're still in probability land. And quite frankly, we should be careful when we start talking about differences and insisting that they exist. Now here we have an example that's relatively benign, whether a person is there or not. But these methods are used to come up with situations in which we can compare two groups of people and say one group of people is better than other groups of people. And again, it's all still probability based. And I don't know if you should say that one group of people is better than another group of people or different than another group of people when there's still a 5% chance you're wrong. Which is why you don't write papers that make you look bad when you want to say that people are different. So the process is we assume through the null hypothesis that the two populations are not different. So x1 minus x bar 2 should equal what if they're not different? Just give me a number, a round one. Thank you. Okay. That's our null hypothesis. Except somebody might have noticed that I wrote it wrong. How should I have written it? The null hypothesis is actually that in the population there's no difference. So instead of using x bar for our samples, I should have said that the average is 0. Both are actually right. I just want to be a jerk about it. But I want you to think about this, because remember, when we're talking about our population distribution, we're testing the difference in the population based off of the difference in our samples. So again, a little quirk there. So you can write it either way. This is our null hypothesis. Okay. We've randomly drawn samples from each population. We've calculated the difference, and although we expect there to be no difference between the sample means because of sampling error, the fact that we have a small sample from the large, we get a distribution of differences. Remember, the 15 cars that we observe could be in a place where there are geographical differences or cultural differences or just a parking lot of really nice people. Where might you find a parking lot of really nice people that want to hurry to be nice to the other people? You guys did not think you'd be talking about parking lots today. No. The nice people go to Target. Chick-fil-A. Okay, I understand you're in a hurry. I am in a hurry. Deliciousness is in my car. All right. I was going to go with church, but, you know, like church, nice people go to church, don't they? Shouldn't they be nice to the... No? Okay, maybe not. Where do jerks go? Are there any parking lots that are full of jerks? Walmart, McDonald's, you guys are racist. Brandish. Nice people go to Target. Assholes go to Walmart. They have lower prices. Okay. About this distribution, we actually already know a lot about this distribution of differences. It's just like all the other normal distributions, right? The mean should be 0. Why should the mean of this distribution be 0? Because our null hypothesis says that there should be no difference between groups. It's symmetrical. It's approximately normal, which means that as it gets larger, it looks more normal, which sounds a lot like a t-distribution. Again, we're dealing with small samples. Just to make this a little bit more confusing, Now when we're doing the standard error, it's the standard error of the difference. So not only are you going to look at what the differences between the two means are, but you're also going to compute a new version of the standard error that takes into account the sample size and also the in-group variation. Just one extra step. Nothing hugely complicated. So if we work the steps. First step, state the null and alternative hypotheses. So our null hypothesis is there's no difference between having an intruder and no intruder and the amount of time that it takes to leave a parking spot. The alternative hypothesis is that the presence of an intruder changes the amount of time. If we do it in a non-directional sense, we can just say that the presence of an intruder changes your behavior. We could go directional. We could say that the presence of an intruder either makes you quicker, because you want to get out of there because you're nice, because you're at Target apparently. Or you could say that the presence of an intruder makes you take a longer amount of time because you're a jerk. And how dare they want your parking spot that you don't want to use anymore. So these are our null and alternative hypotheses. Again, the book uses the muse. I'm fine if you use the X bars, whatever. Tomato, tomato. They mean essentially the same thing. Let's make a decision about the null hypothesis. Let's do a hypothesis test. What do we need to remember? Well, there's this thing out there called degrees of freedom. We have to set our decision rule. So how much probability do we want in the tails? We always want 0.05 in the tails. We're going to calculate our test statistic. Most likely it'll be a t-test. T-test for independent means. Does anybody need a t-table? We'll calculate a t-score and decide whether or not to reject the null hypothesis and look at how if it's significant or not. First step, degrees of freedom. Okay, so we have 30 observations total, but we're generating a sample mean from each group. So we're actually calculating two statistics. We need to take out 2 degrees of freedom from each group. So the way that this is done is the degrees of freedom equals the number in the first group minus 1 plus the number in the second group minus 1. Professor Wood, why didn't you just say n minus 2? Because there are situations in which you will have data where you have unequal numbers in each group. So I might have 30 no intruders and 10 intruders because our parking lot apparently is never full. So it's harder to collect data when there's no intruders. Or when there are intruders, sorry. Does that make sense? So that's why we're going to do it this way, because this way will account for unequal sample sizes. In this observation, we had 15 intruders, 15 no intruders, 30 total, 30 minus 2, twice. All right, it's 28. So degrees of freedom is 28. Thank God I have an example that is an even number of degrees of freedom, because that's the chart I gave you. Okay, so if I look at degrees of freedom for 28, and I know my decision rule is I want 5% in the tails, what is going to be my critical value of t? Sammy? I just gave it to you. I just handed it to you. We have 28 degrees of freedom, so go down to the 28 row, and I want 5% in the tails. Which column are you going to use? Look at the very top with 5% in the tails. How many tails do we have? Right. This is the, yeah. So here's the trick with the t-table. Remember, how many tails are we testing? 2. So how much are we going to put in each tail? Right? We're going to have 2 over here, 2.5 over here. We're going to have 2.5 over here. We always look at the picture at the top. Yeah, we're going to use the middle one. Okay? Always make sure you understand the picture on the top versus the picture you're going to draw. Because if you like me, every time you have a situation where you're using a distribution, you will always draw the distribution out. If you don't like me, well then you're just going to get it wrong anyways. Okay, so let's think about this for a second. We have our distribution. We're going to go with a non-directional alternative hypothesis. We just want to know if people behave differently. Because I have competing theories as to how differently they behave. Right? Either they want to be nice or they want to be mean. So I just want to know if people behave differently. So I'm going to take that 5% and I'm going to put it in each tail, which means I'm going to split it in half and put 0.025 in one tail and 0.025 in the other. So if you have your table and you want to put a little star over that column, so you're like, there's something about the column I need to use, you might want to do that. Hint, hint. You also will get a hint because if you look at the very bottom row, that little infinity sign, it goes out to 1.96. And that's a magic number for the z-score. Okay? So you'll have heard that before. Another little hint on how to use that t-table. Okay, so our alpha is going to be 5%. Identify the critical values. The critical value on the t-table is, this is t, 2.048. So if we get a t-value that is greater than 2.048, we're in the region of rejection, which means it's really rare to observe this difference if no difference truly existed in the population. In fact, we would say that there's a less than 5% chance you would get this difference in our sample when there's no difference in the population. Just going to keep saying it different ways till I see some heads go, oh yeah. That makes sense? Thank you. Because I ran out of ways to say it. So we know the t we're looking for, but now we have to calculate it. Calculating this t is the same as we've done for z-scores. The difference between our two averages divided by some measure of variation. So the difference between the mean in our first group and the mean in our second group, so you can, this is where we get our difference of 9, divided by the standard error of the difference of sample means. Guess which one we actually have to do some work on. It's that bottom one. This takes place over many slides. I've had students complain, you shouldn't do math on slides. Well, can't help it. It's the only way to record it. So let's take a look at this equation. To calculate the standard error of the difference of our sample means, this is what we do. We take the square root of S1 squared divided by N1 plus S2 squared divided by N2. What are these S1 and S2 squareds? These are the variances, right? Remember, S squared is the variance, S is the standard deviation. These are the variances within our sample means, each group. So back to week 4, when we learned about how to calculate a variance and a standard deviation, that's that. That's that S. That's that S squared. The only difference is I have this subscript for telling you which group it's from. Okay? So S squared of group 1 are those 15 observations from the people who had intruders. S squared of group 2 are the 15 people who didn't have an intruder. Okay, so this is nothing new. This is week 4. Again, we want to include the 2 different sample sizes because we want to recognize that we could have unequal groups. So N1 is just the number in group 1 and the N2 is the number in group 2. Because I don't want to be here for 3 hours while you guys add and subtract something 30 times. We just gave that to you on an earlier slide. So looking at the equation, you plug in the numbers you have. We got a number squared. You would do that first. So you would do your exponents first. Then you would do your division. And then you would do your addition. And as long as you don't screw up your calculator, the answer is 3.74. Question? Is the S squared the... No, the 15... This here? This is the N. N1 and N2. That's our sample size for each group. This number is the standard deviation for the group. When you calculate it, so if you were to calculate it by hand, remember how you calculate a standard deviation? You first calculate the variance and then you do the square root of the variance. You wouldn't have to do that and then re-square it because you would have it as S squared. So we calculate it through. Again, we have our difference between the sample mean of group 1, the sample mean of group 2, the standard error of the difference between the sample means. The difference was 9.06 seconds. We divide that by the standard error. Our t-score is 2.42. So looking at the t-score, what do we think we're going to do with our null hypothesis? Louder. We're going to reject the null hypothesis. Why, Allie, are we going to reject the null hypothesis? Because it's in the region of rejection, which means that it's very what that we have observed this. It's very unlikely that we have observed a difference of 9 seconds if in the population there should be no difference. So our t-score that we've calculated of 2.42 is greater than, remember the alligator eats the bigger meal, the bully points at the smaller kid, bigger, smaller, therefore, 3 dots means therefore, we are going to reject the null hypothesis because the probability is less than 0.05, less than 5% chance. It's really, really rare to see what we saw when there's no difference. Really rare. Less than a 5% chance. So the critical value, if we wanted to be even more stringent, which again, this is just something scientists do because they're idiots. They look at the difference between 5%, 1%, and 1,000th, so 0.1%. We did not reach that level of significance, but again, it's either you're significant or you're not. Don't worry too much about the levels of significance because it's less than the 2.7 critical value. So it is significant at the 0.5 level, but not the 0.1 level. I think this must be a sociology thing because we really don't pay this much attention to it in political science. To show this to you graphically, because remember, you're following my instructions, you're drawing out the curve in the beginning, Here is what we observed in our sample, 2.42. We are in the region of rejection. There we are. Okay. Draw a conclusion. The mean departure time for the 15 drivers in the intruder group. Notice that we're talking about our sample. We're not necessarily generalizing about the population, because we're talking about what we observed. So the 15 drivers in the intruder group is significantly greater than the mean. And what do I want you guys to do when you think about significance? What kind of significance is it? Statistically significantly greater than the mean departure for the 15 drivers in the no intruder group. All right. Again, people have a hard time understanding what that word significant means. Because if you have somebody that doesn't understand statistics, they're going to make the argument, and I've seen this happen at conferences, and I cringe every time, well, really 9 seconds isn't that significant. I mean, come on. It's just 9 seconds. Oh, that's not what we're meaning. We're not meaning that we've changed somebody's life over 9 seconds. That's not what we're saying. We're saying that it's statistically significant. That this difference that we observe is unlikely to exist in a world where there is no true difference. So this is what they wrote in their article. The present series of studies is consistent with prior findings that people display territorial defenses in public territories. What is new about the present research is that it suggests people sometimes display territorial behavior merely to keep others from possessing the space, even when it no longer has any value to them. Okay, so there's two things here. One, we are territorial over things that we do not actually own. So there's obviously a previous literature that has looked at these things. Which is true, because I get upset when somebody parks in my spot in the parking lot. That should sound familiar to some of you. Right? No, this is my spot. Dude, it's a driveway. Right? Like, there's an order to things. At my house, guess which spot is mine? It's the one on the right. It's my spot. In the right, close to the garage as possible. My spot. My spot. Now, I actually happen to actually own that spot because it's at my house. But why do I have a spot in this parking lot? Do I own the parking lot? I just work here. You move my office, I'm going to have to move my parking spot. In fact, my parking spot is now relative to where my office is. Because my parking spot used to be over there when my office was on that side of the building. But now my office is on this side of the building, so now my parking spot is on this side. My spot. I don't even own it. Anybody here have their spot or their preferred place to park at a spot that they go to frequently, but they have no ownership over? Like where? Like, tell me, don't make me to be the only silly person here. Like, tell me, share your experience in what you own that you don't really own. The seat. There you go. Yep. It messes everybody up. It messes me up because I'm expecting you to be there. Like, you're normally there. Austin. Right? That's your spot. That's your spot. So when I look up, I'm looking for you there. You move around a little bit, not too much, right? But don't you hate those people? Like, actually hate. Like, I hope you fail this class. You're in my spot. Right? You might kick them as you're walking by. Oh, I usually sit here. Sorry. Kick them in the shins. Okay. So this is not a made-up thing. This is scientifically studying and coming up with an explanation as to why we behave the way we do. And we do it. I did it this morning. I'm driving down the road. I just passed through a school zone. The limit after the school zone is 35, and I'm going 35, and it's not fast enough for somebody behind me. So what did I do? Nope. Put my foot off the gas and slowed down another 5 miles an hour. So the person who wanted to go 40 in a 35 will now be going 30 in a 35. I did not slam on my brakes, which is what my dad would have done. Brake check. Don't do that. All right? Don't put your foot on the brake. Just lift up the gas a little bit. Teach them a lesson.
I do both.
Don't brake check.
I know, I learned that the hard way.
Don't brake check.
I got almost run off.
People get really, really angry when you brake check them, and they may or may not smash into the back of your car. Okay? I didn't care about his time. I care about my time. All right? Plus, we were in a school. Well, we were just out of a school zone. All right? And it was clearly 35. I do the same thing on international. If anybody drives on international, the limit there is 45. I'm not going over 45. I don't care how empty the road is. I don't care how straight it is. The limit's 45. If you're behind me, you're going 45. I don't want to hear it. Okay. Roads have no value to me. Time is the only thing that I have value in, but still, I behave that way. And I don't really care. Like, just the things we do. Okay? But there's a reason behind it. We're displaying some sort of control over territory, even though it's not our territory, because we think we're using it better than somebody else. Okay. I don't want to do that. I don't want to do that. I do want to show you one more example, and I've got the time. Again, going back to this idea about how students in elementary schools perform. This one is actually, I think this one's ridiculous. But then again, I think gym is kind of ridiculous. No offense to any parents or any children of gym teachers out there. Here's a study, a real study, comparing the ability to jump rope. I don't know why jumping rope is a thing. It's a thing. It's some form of exercise. I get it. It could be hard, whatever. All right. So the effects of exercise intervention on kindergarten and first grade students. So this is John territory. John's in kindergarten. And his ability to jump rope for 30 seconds. Lazy kid will not be jumping rope for 30 seconds, trust me. Unless it's jumping rope off the couch onto something, because he won't stop jumping off the couch. Compared these to a control group who did not receive the intervention. So I'm just imagining, like, there's a group of kids who are receiving an intervention and being taught how to jump rope. And then there's a group of kids where you're like, you hand them a rope and be like, jump over this repeatedly. And they've never done it before. So I'm hoping the kids who have been taught how to do something can do it better than the kids who have not been taught how to do something. Just a thought. But here we have two groups of different numbers. Right? So the kids who were taught how to jump rope or receive the intervention, whatever it is, there were 16 of those. And there were only 11 kids, I don't know, maybe they were absent that day. They didn't receive the intervention. So here are the two sample means. It looks like the intervention group, which can do 27 somethings, is a lot higher than the non-intervention group, who can only do 12 somethings. we state the null and alternative hypothesis. The null hypothesis says that the intervention group and the control group should be the same. If it has no effect, there should be no difference between the two groups. The alternative hypothesis is that we had an intervention and it should improve the students. First step, calculate degrees of freedom. Again, to point out that we have different sized groups, but because we've written the equation in a way that accounts for that, we just plug in the size group numbers. So we have 27 participants, which means we have 25 degrees of freedom. We're going to set our decision rule. Oh, 25's on here. So for a two-tailed test, degrees of freedom of 25, the critical value is, middle column, 2.060. Got it, Sammy? If the t-score that we calculate is outside of those numbers, we'll reject the null hypothesis. We'll calculate t again, same exact way. Right? So the fact that we have different sample sizes does not change how we calculate t. It does make this just a little bit different. So here's what we have to do when we're calculating the standard error. This looks god-awful, but it's really not. Because again, it's all things you already know how to do, and if you just take it one chunk at a time, it'll be fine. But here's what we're doing. So we got a little bit more complication up here. And the reason that we have the complication up here is because we have to weight the contribution of each group's variance to the standard error by how many are in the group. Okay. So I'm going to just, those of you who are slide copiers, I'm going to let you finish that equation, and then I want to go back. So nod or giggle or wave your hands in the air if I can go back to a slide. Cody's still going. Austin's doodling. Waiting for Allie again. We good? All right. So let's go back. Let's take a look at what it was without. Okay. This was a lot easier. Right? We just had these little 4 numbers here. Okay? It was a lot easier. What we're adding is weighting these measures of variance from each group. So we're doing that. And you'll also notice in the denominator, right, we had the numbers of the two groups because they were providing equal weight. And now in here, we have the numbers of the two groups minus 2 more degrees of freedom. Just go with it. Okay. And then finally, we're taking this whole measure of variance and weighting it one more time by the proportion of the number of observations. So it's just 2 extra steps, and it is a little bit wider on your page. But again, nothing here that should be mathematically difficult for you to do. And as long as you have the numbers, when you plug them in, it just looks like this. Right? So 16 in the first group minus 1, parentheses, times our variance squared, plus, same for the other side, divided by adding and subtracting. All right. So what we would start, we would just, again, remember PEMDAS. Abby's got some other thing for this. I forget what she calls it, but I need to beat that out of her. All right. So first thing is whatever's in the parentheses. We have this thing here and this thing here. So we'll do that first. The next thing is the exponents. We'll do this one and this one. Here's your multiplication. There's multiplication here. And then it's just addition and subtraction, which can all be done in one straight across the way. Okay, it's nothing hard. This is just awful because it has a fraction. Just turn the fraction into a decimal, everybody will be okay. Which when your third grader is learning fractions, she really doesn't like it when I tell her just ignore them because they have to learn what they mean. We got into a fight last night about it. Go through, do all the math, and there you go. You end up at a single number. T-score is the same. So we have the difference between the two groups divided by that god-awful standard error we just calculated. Oof. Takes like a whole sheet of paper. But you can do it. What's our T-score? 3.97. We should by now start to develop an inclination. Because look at that table. The T-table for that column. Where's the button I want? There we go. Full screen.